Hey guys, in this video we're going to talk about elastic collisions. Now you should probably recall that in general for collisions we're going to say that momentum is conserved, which means that for pretty much any collision problem we're going to write the conservation of momentum equation. That equation should look very familiar because we'll use it for pretty much every kind of a collision or explosion or anything else that we've done in this unit. Now, up until this most recent homework, we've only actually done inelastic collisions and explosions. During an inelastic collision, kinetic energy is lost. That's what makes elastic collisions special. Since kinetic energy is conserved, there is a second equation which we will always write for this type of collision, which you can see below. So that means that if we're talking about a question with an elastic collision, there are two equations which you're going to write, and they are this one that you're very familiar with, and then this one, which is saying simply that the kinetic energy before the collision is equal to the kinetic energy after the collision. All right, now, a couple of things. They have to say that it is an elastic collision. That word must appear in the question. So they have to say something like, two particles collide elastically, or if the collision is elastic, what will the final velocity be? So something that says that it's elastic. Otherwise, don't assume. Okay, momentum usually is going to be conserved, right? We've been writing this equation over and over. Yes, yes. This one you only write if they say elastic. If they don't specifically say that the collision's elastic, do not write the conservation of kinetic energy equation. All right, let's do an example of an elastic collision so that you can see how one is typically going to be set up and worked out. And if at any point you think this is difficult, you should just remember that it's... So this is a typical question where they'll give you something like one card collides with another. They specifically say elastically. Remember, that's important. That word has to be in there. And then elastically means they're going to bounce off of each other, right? They don't stick together or anything like that. Typically, elastic collisions, since no kinetic energy is lost, are very bouncy. I realize that's not a very technical term, but observationally, that's what they look like. Okay, now if they have said elastically, remember, start off with, write down the two equations that you saw on the previous slide. I'll do that. Okay, so we have momentum is conserved, kinetic energy is conserved. All right, so I've written the equations, but of course, we're going to have to make substitutions into them. The first cart has a mass of just little m, and it's moving with, let's say, a speed of, call it v, or v naught, or whatever. Second cart is stationary. All right, easy. And then after the collision, well, we don't know either final velocity. That's one common feature that you're going to see in elastic collisions is both of the final velocities are unknown. All right, having two unknowns makes the algebra more complicated, which is why we left this till a later homework assignment. Okay, but that's what we have so far. Key point here, when we say M2, say is 2m, very often people will goof when plugging in for that. They'll just put m or whatever. I am typically going to give you questions where the masses are some nice easy ratio like m and 2m or m and 3m. It's just a lot easier when they are a nice ratio, okay? Also, believe it or not, this is easier symbolically than it is with numbers. With numbers, the algebra gets really gross. So it's actually simpler with symbolic questions. All right, next line down. If I am looking carefully, I should notice that there is an m in every single term here, so I can cancel out the m. And then I will have, next line down. All right, that's as far as you can get using momentum alone. Since we have two unknowns, we can't solve for either one, and therefore we now need to use our kinetic energy equation. All right, I'm going to now substitute in similarly into the kinetic energy equation, plugging in the masses and velocities from the diagram. there are a few things that I should notice are in every single term. One would be, well, there's a 1/2. Well, let's just get rid of that. Don't even need that. And also notice, just like above, there's a factor of m in every single term. Okay, so rewriting that simplified equation, well, that also has two unknowns in it. And so it would perhaps seem like I'm stuck. However, no, not really. I'm not stuck because I have two equations, two unknowns, and therefore I can solve using substitution. All right, now, please note, if you think you've found an algebraic shortcut, you haven't. I'm sorry, there's not really a good shortcut on this question. You just have to do the substitution and then just kind of crunch your way through the algebra. That's just how it's going to go. Easiest way to do this, though, is take our momentum equation and solve it for V1 final. So if I do that, it's V1 final equals, let's see, V minus 2 V2F. All right, and then I will take that and substitute it in for V1 final down here. When you do this, please note you are going to use FOIL, as you learned back in Algebra 1. So careful when you do it. If you like, pause the video, plug it in, expand using FOIL, and then resume the video to make sure that you got it right. All right, immediately after substituting, that's what I have. After foiling, I get these three middle terms here. Now I've just got to combine like terms. And some nice algebra things happen, like, for example, I'll subtract v squared from both sides. Those disappear completely. And then moments later, I have this expression. My apologies, I just noticed an error in the line above, which has been blotted out now. Okay, so fine, I get this expression. And notice there's a V2F on both sides. I'll divide both sides by one factor of V2F. And so now it just says 4V equals 6 V2F. Well, divide both sides by 6, and you will have that V2 final is 2/3 V. Now, what does that mean? Well, that would be the final speed of that cart up there. So the 2m after the collision is moving with the speed of 2/3 of whatever the first cart's initial velocity was. Well, if you want to know the final velocity of the other cart, all you actually need to do is take your answer here and plug it into really either of the two equations that you had from above. But if I take it and plug it in for my expression for V1 final, again, you can do the algebra on your own to verify, but the answer you will get would be negative 1/3 V, meaning it bounces off and it's going at a speed of 1/3 of whatever it started with. I did draw it bouncing off in my diagram, but that was an assumption. Sometimes after these collisions, it will continue to move to the right, and that's just how those go. All right, I am going to set up another question and not really talk it through, but just kind of show you the algebra for a slightly more complicated problem, one where it's the heavier cart in motion. If the heavier cart is in motion, the algebra is a little bit more complicated, but not beyond what you're able to do. I just feel like maybe you need to see it worked out in front of you.